So we've seen the common specimen preparation methods and how a specimen is introduced into the microscope column. And we've also seen some demonstration of basic imaging to obtain what is called as a bright field image. In a transmission electron microscope, when you're illuminating a specimen with a broad cylindrical shaped electron beam, when I say cylindrical, it is having a parallel beam illuminating sort of a small area of a specimen, and the cross section that is interacting has a sort of a cylindrical shape. You call this as the parallel mode illumination, and this is the basic first step that you see. You search for an interesting area within the specimen, and once you have your area of interest, you start obtaining images by inserting different apertures, and you orient the specimen in different orientations and start getting more and more meaningful data. Before we understand what kind of imaging methods you can use and what are the different types of contrast mechanisms, I would like to draw your attention to the most important phenomenon in electron microscopy, which is the electron beam and specimen interaction. When a fast moving electron beam, if I call it as a fast accelerating charged particle, which is in fact electromagnetic radiation, when it collides with a specimen, there are a range of signals that are generated as a consequence of this collision. We term this interaction as scattering. When you have the same kind of a phenomenon happening in light, when light passes through transparent objects, in fact when you have lenses or cylindrical, when you have lenses or rectangular blocks or a prism, you might either have dispersion or refraction of light. Refraction is simply bending of light due to changing in the refractive index. Whereas when you have a charged particle or an electron beam, you have various possibilities which can cause a change in the wavelength of the moving electron beam, or they can deflect or deviate the charged particles, and which can introduce a phase shift in the electron beam propagating direction. To understand all of these kind of interactions, let us start by looking at what are the various signals that are generated. One important distinct terminology that I'd like to introduce here is when I converge a specimen when I converge the electron beam to a sharp point to interact with the specimen, I call this as a probe, and the incoming electron beam probing the specimen is called as a probe, and the information that I get out of the specimen, the different kinds of signals I get, are called as the signals. Let us look at most common signals that are generated in a transmission electron microscope. When a fast moving electron beam is incident on a specimen, you generate a range of signals. These signals are typically generated in all the three dimensions, like a sphere from the point of interaction within the specimen. However, for a matter of convenience, we have written them in this order. It is not exclusive that these signals are only generated at these angles indicated here. The arrows and the directions shown here are only indicative. So one of the first kind of signals you see is called as secondary electrons. So when an electron beam strikes an object, you can cause excitation of loosely bound electrons within the sample, within the material, and they are ejected out as secondary electrons. These secondary electrons are commonly used for imaging in a scanning electron microscope. Likewise, you also have the generation of something called as backscattered electrons. When we look at the phenomenon of interaction of an electron beam with an isolated atom, we will try to understand what these two phenomena are. But nonetheless, when an electron hits a specimen or collides with a specimen, you can also generate secondary or backscattered electrons. There is something called as Auger electrons. The Auger electrons can be created because when an electron beam knocks out one of the electrons from one of the shells within the material, you can have intra-band transitions which happen, and the result of this kind of a transition could either be emission of an X-ray, which is called as a characteristic X-ray, or you can have an electron being emitted itself. For example, I have various K, L, M, N shells of, let us say, a transition metal. You may have release of electrons due to one of the incoming electron beam knocking out the electron from one of the outermost shell, and if an electron transitions here from the inner shell to the outer shell, as a consequence of this transition, you may have the emission of a characteristic X-ray, or it is vice versa. One of the electrons being knocked off from the inner shells may have the other kind of transition. You could have transition between various energy levels within the electron as well, and associated with this, if the emission is an electron, you call it as an Auger electron, or if you have the emission of an X-ray, you call it as a characteristic X-ray. The Auger electrons and characteristic X-rays have a specific energy associated with the transition that are happening within a material, and you can use these as signals. So these are essentially inelastic scattered signals, and there is an energy associated with these, and using these you can kind of identify which elements are present within the material. You may also have the emission of visible light. There is a technique called as cathodoluminescence, where the visible light is used, typically in semiconductor materials. Because of electron hole recombinations, you may have emission of visible light. You will also have a significant portion, in fact in transmission electron microscopes it may not be extremely high, but you still have some absorbed electrons as well. And you have something called as the Bremsstrahlung X-rays. These are also used for understanding. So this is kind of the background X-rays, unlike the characteristic X-rays which are always produced from a sample. There are methodologies in where you are using this Bremsstrahlung X-rays to look at bond strength in some specific carbonaceous materials as well. A large portion of the signal for the electrons that have interacted with a specimen which transmit through are contained very close to the optic axis, and these are elastic scattered electrons, or the beam that is going along the principal axis of the electron microscope, you call it as a direct beam. I'd like to draw your attention to one common mistake we usually make. The beam traveling along the optic axis, some people call it as the unscattered beam, perhaps because there is no deviation in the trajectory of this electron beam which is going along the optic axis is called as an unscattered beam, but it is actually wrong. This also undergoes some scattering, but there is no deviation in the path. So you call this as the direct beam. So be careful with the terminology you use. You do not say there is nothing like an unscattered beam here. When a 200 or a 300 kV electron is hitting a specimen, there is always some scattering and some interaction, and the signals you generate are a consequence of this. You also have the inelastically scattered electrons, and these are used for, again, analytical. This is again used for an analytical technique called as electron energy loss spectroscopy. We will start understanding all of these scattering phenomenon in the next slides, and we will see, depending on what kind of signal you are using to retrieve useful information from a specimen, we will look at more details on these different signals. Now, we use most of these signals for different kinds of imaging techniques in a TEM. And if I look at the ray diagram of a microscope again and look at different signals that are generated and different modes of imaging that you have, most commonly a basic TEM, you call it as a conventional TEM, and you could operate in all these modes. If you are imaging using a parallel beam, that is if I have a specimen which is less than 100 nanometer thick. You've seen in the demonstration that I can converge the beam to a probe, or I can spread the beam to fill the entire screen. So when I have the entire large portion of the specimen interacting with an electron beam, I can call it as imaging in a parallel beam, or I could have some special techniques where I converge the beam at a specific angle. But the idea here is I'm not forming a probe, and the entire area of interaction is being collected on the fluorescent screen or your detector at one go. In this mode of imaging, you commonly have bright field imaging, dark field imaging, high resolution TEM, and if you have the attachments, you have other special modes like electron holography and so on. The other mode of imaging, where I converge the beam to a small probe, where my interaction volume is confined to a very small region, and I raster the electron beam. So in the parallel mode of imaging, there is no raster, but when I form a probe, if this is the top view of the specimen, I recite the beam at every point and I collect information pixel by pixel on the detector and I form an image. This is called as scanning transmission electron microscopy. And once you form a probe, you have different modes called as annular dark field, high angular dark field, bright field STEM, and there are a few more advanced methodologies called as differential phase contrast imaging in STEM or 4D STEM. There is one more special mode where you have something in between a parallel beam and a probe. You can form sort of a truncated cone shaped beam, and you have a special mode called as convergent beam electron diffraction. And if I have such a truncated cone and I use special beam coils to precess the electron over this point, you also have a special methodology called as precision electron diffraction. So the idea is I form a probe, but the probe tip is not really sharp. You have a slight width to a slight diameter to the probe tip, and you intentionally precess the probe with a small kind of an angle, and you can collect the information from a sort of a truncated conical area from a specimen. All these methodologies give you different kind of information from the specimen, and essentially you get the compositional, morphological, crystallographic structural information from a specimen. Combining all these things together is only possible in a transmission electron microscope, and this is what makes it a very attractive technique. This is considered one of the most powerful characterization techniques because you get information not only on the structure, morphology and size of the specimen that you are using. When I talk about size, these could be grain sizes or crystallite sizes, however you define it, but you also get the corresponding crystallographic information. You can use special modes of imaging to look at defect structure, and you can do a lot. Now let us look at what commonly happens when electrons are interacting with matter. I have defined this broadly as scattering. So when I was introducing the concepts of an image and lens, we've seen that an image is called as a two-dimensional distribution of intensity, and a diffraction pattern can be considered as a radial distribution of intensity. So if I have diffraction patterns or images in a conventional TEM, you can initially capture them on the viewing screen, you record them with optimum imaging conditions on a CCD camera, which is typically just outside the column of the microscope, and you insert it into the column of the microscope. It's a retractable camera that you commonly use. When you have analytical signals like EELs and X-ray spectra, This is again transferred to a detector which is retracted and inserted into the microscope column. When you see one of the forms of imaging called as backscattering, you can use this for topographic information and also relative atomic number differences within a scanning electron microscope. If I define the characteristics of scattering within an electron microscope, or the characteristics of scattering when an electron beam interacts with a specimen, you can control the scattering by the energy of the incident electron beam, the atomic number or the weight of the scattering atom, thickness plays a major role, density, crystallinity, and the angle of the specimen to the incident beam. You may have grazing incidence in some cases. It is commonly used in X-rays, but there is something called as low energy electron microscope where you are collecting signal only from the surface. So there are different ways in which you can orient the specimen and collect the information. The angle of specimen to the incident beam also influences something called as channeling contrast, and there are special modes of imaging which are relying on this. If I look at scattering in TEM in general, I can classify scattering based on the angle of scatter. As a consequence of strong interaction of electrons with matter, you have something called as forward scattering or backward scattering. If I have a specimen like this, and if I have an electron beam incident perpendicular to the specimen, and let us say this is along the principal axis of the microscope, all the angles of scatter, so if I define the angle of scatter, so if the signal is generated like this, let us say this is from the incident beam, and let me call this as psi 1 and this is psi 2s. I can define an angle of scatter alpha here. It is typically a semi-angle. When I wrote this psi 2, there would be a complementary psi 2 prime here as well. I am only looking at one half of this. Depending on this angle of scatter, if alpha is less than or equal to 90 degrees, I can call it as forward scattering, and once alpha exceeds 90 degrees, I have the backward scatter. The direct beam, like I was mentioning, is a type of forward scattering. Most of the elastically scattered signal, which is the electrons which have not lost any energy as a matter of interaction, are also forward scattered. In a transmission electron microscope, you have something called as the Bragg's diffraction. The diffraction signal, if you recollect where the diffraction signal is, it is at the back focal plane of an objective lens, and you use the information from the back focal plane as an object plane for the projection lenses, and you collect the diffraction pattern. We will look at diffraction in more detail at a later stage. And there is a minor correction here. Refraction is commonly observed when you have light interacting with transparent or lenses or transparent materials. So I apologize. I was talking about scattering in TEM alone, but like refraction, you would have bending or change of phase of an electron beam when it interacts with the specimen. So refraction is a kind of scattering again in optical microscopes, but sticking to the signals in an electron microscope, you have largely elastic and inelastic scattering. If I classify the scattering phenomenon based on the energy of the signal that is produced, I can classify them as elastic scattering or inelastic scattering. In elastic scattering, there is no loss in the energy of the scattered electron beam, whereas the inelastic signal has a measurable loss of energy. Please bear in mind there is this quantity called as measurable. So depending on the scattering phenomenon and the angle of scatter, if I am able to collect the signal that has lost some energy, and if I classify it as an X-ray or inelastically scattered electron or any other inelastic signal, I can use it for fingerprinting of the specimen or use it as an analytical tool to know what is inside the material. The other classifications of scattering are based on the kind of interaction that is happening. In fact, this is a commonly used terminology. You look at electron as a wave or a particle, but in reality you cannot distinguish them. An electron that is propagating inherently behaves like a wave and as a particle as well. So based on the wave nature, when you've seen the discussion on electron sources, we've seen something called as coherency. So if the electrons that are scattered all have the same phase, so the scattered electron has the same phase as the incident electron, you call it as coherent scattering. When there is no phase relationship between the incident and the scattered wave, you call it as the incoherent scattering. Based on angle of scattering, like I just defined a short while ago, if my angle of scatter alpha is less than 90 degrees, I call it as forward scatter, and if it is greater than 90 degrees, I call it as backward scatter. If I look at the nature of scattering, you have elastic scattering again, which is one form of coherent scattering. Usually you can relate this scattering phenomenon to the angle of scatter. When I define Rutherford scattering and scattering cross sections, we will look at this in more detail. But most of the signal that is elastically scattered, or when you are looking at forward scattered electrons, they are typically less than 10 degrees or 10 to 20 milliradians. If I see the inelastically scattered signal, it is more or less incoherent, and as you have more and more thicker specimen, you have more pronounced backscatter, and there are specific angles that you can associate with this inelastically scattered signal, and based on this you can position the detectors as well and you collect the signal. Having an idea on the direction of the inelastically scattered electrons or X-rays. In fact, X-rays emanate all across the 3 dimensions of a specimen. This is usually helpful in designing the detectors and positioning them and where they enter close to the specimen to collect the optimum signal. If I look at the other methodologies of classifying scattering, based on the number of events of scatter that happen, you can also quantify them as a single scattering or kinematic scattering, or dynamic scattering, or plural or multiple scattering. More often than not, when a fast moving electron beam is interacting with a thick specimen or a specimen which is even 100 nanometers thick, you can have more than one scattering event. So based on the number of scattering events, you can classify scattering into single scattering, you only have one scattering event, or plural, which is, let us say, 2 to 3 or 4 scattering events, and you have multiple scattering or dynamic scattering events. These ideas of scattering, looking at the particle nature of electromagnetic radiation, most of them have origins in the X-ray diffraction. Typically, X-rays which are not as strongly interacting as electrons tend to have only kinematic or single scattering event, and this terminology also has its origins in X-ray scattering and X-ray diffraction. Most of charged particles which are interacting with matter, you can still quantify them based on these scattering classifications. So scattering based on energy, based on angle of scatter, based on the wave or the particle nature, which in my opinion should not be distinguished. They are two sides of the same coin, or based on the number of scattering events. You've come up with various classifications, and in the end a consequence of all of these scattering events is causing either a change in the angle of propagation of the electron beam, or in turn it results in change in the phase and the amplitude of the electron beam. So most important in most of the optical techniques, or in electron, or for example neutron or X-ray based techniques, is understanding the intensity and the phase of the incoming probe and comparing with the signal that you collect and formulating an understanding based on this. And this forms the foundation of understanding of a few principles called as scattering cross section or probability of scattering, and this forms the foundation of electron matter interaction for a transmission electron microscope, or this forms the foundation of electron matter interaction for electron microscopy in general. Based on the technique that you are looking at, whether it is scanning electron microscope or transmission electron microscope, you look at specific signals, and the interaction phenomenon is all based on the same, which is having origins in the famous Rutherford scattering experiment, where you've classified a scattering event based on the angle of scatter. So we've seen scattering based on the number of scattering events, or based on the angle of scatter, or based on the energy of the beam, that is based on the energy that has been lost as a consequence of the scattering event. Moving on, we will look at how the scattering is when I have an isolated atom, when an electron beam interacts with an isolated atom, in the next lecture.